When we left off in the last video, we just completed the top portion of this chart, which is allowing us to consider SN1, SN2, E1, and E2 mechanisms given a particular substrate structure. Now we're ready to add allylic and benzylic substrates to our table. Before we add allylic substrates, I'd like to go into their chemistry in a bit more detail. Let's use a biological example. This compound, dimethylallyl pyrophosphate, is a precursor to steroids in biochemical pathways. This pyrophosphate group, or the two phosphates linked together, can be thought of as X, just a good leaving group. It's widely accepted that this pyrophosphate group leaves on its own, and in this SN1 reaction, forms a primary allylic carbocation. This is possible because there's extra stabilization in this molecule. We can draw a resonance form that shows a tertiary carbocation contributing to this structure. This extra stabilization promotes the ionization by SN1. However, the side containing the tertiary carbocation shown with this resonance form is significantly sterically hindered. Therefore, nucleophiles end up adding to this carbon atom to give products like this. I think this example does a pretty good job of highlighting some of the subtleties here. We might not think about this as ionizing to form a primary allylic carbocation, but when we examine the resonance, we can see there are other factors going on that makes the ionization favorable. So, allylic substrates, even when primary, but usually under special circumstances, have the SN1 mechanism available to them. So if you're given a primary allylic substrate with a poor nucleophile under these polar protic conditions, I would think that your instructor was kind of leaning you toward an SN1 situation. Especially if we have some branching here, we'll have resonance stabilization as we've shown, and so the major mechanism for the poor nucleophiles is going to be SN1. Now E1 is not a possible mechanism. We can't deprotonate the sp2 carbon atom here. We'd need a branch coming in this direction to have any elimination whatsoever, and so SN1 is going to be the only mechanism here. Weak bases, and strong hindered bases are going to tip this toward an SN2 mechanism. Again, since elimination can occur with this substrate, we'll predict SN2 across the board. Next, we need to consider primary benzylic substrates. Okay, back to another little aside. Before I add benzylic substrates to our table, I want to go into a little bit more about them as well. Benzylic substrates have electronic effects that can extend from substituents that are on the ring all the way over to the leaving group to determine whether we'll see an SN1 or SN2 mechanism. Let's look at an example. Here we have a paramethoxy-substituted benzyl chloride. Let's imagine treating this with NaSMe. In our chart, we saw that weak nucleophiles with primary substrates tend to go SN2. But this reaction does not. The methoxy group can donate electrons into the ring, pushing out the leaving group and promoting an SN1 mechanism. Let's draw our lone pairs of electrons on oxygen, and now we can show resonance through the whole benzene ring, pushing out our leaving group in an SN1 fashion. This gives this intermediate, which can then be attacked by our nucleophile, giving our substitution product. So we can say that electron-donating substituents, particularly those para to the benzyl group, will promote SN1 reactions. Now by contrast, para-electron withdrawing groups will promote the SN2 mechanism under the same conditions with the same nucleophile. Let's look at why. We'll use a similar substrate, just swapping the methoxy for a nitro group. Now this nitro group is pulling electrons from the ring, both inductively because of this positive charge on the nitrogen, and we can show a resonance form that just shows how profound the resonance effect of this electron withdrawing group is. If we push our electrons like this, we'll get a resonance form that shows that we have carbocation character, a little bit of delta positive character here at this carbon atom. Now imagine trying to make this chlorine leave on its own. We have all this positive character here. We're trying to make a carbocation here that's going to be really high energy. So substrates with this para-electron withdrawing group tend to favor the SN2 mechanism, even though they're giving a similar product. So coming back to our chart, again with primary benzylic, we don't have the option of elimination. We'd need to eliminate from a carbon coming off of here, and that is not present. So I'd say this follows a similar pattern to the allylic substrate. So we're not going to add anything here. This will just be for the two of these. However, remember we did see a case where even with a weak base, we had an SN1 mechanism because of ring electronics. So let's just make a little note. So we should consider our ring electronics, because that weighs into the substrate structure, as the most important factor in determining this. But for a simple unsubstituted case, I would predict this reactivity pattern. Next, we need to consider secondary allylic and potentially tertiary, which I'm showing with this maybe little dashed line here. And let's consider the secondary and tertiary benzylic with this case as well. Now we have extra stabilization of a carbocation that would form here from the extra substituents. When treated with a poor nucleophile, I would predict again SN1, but we have to acknowledge that E1 can compete here as well. Now again, with our strong bases and strong hindered bases, we have the option for E2 elimination again, because we have these groups coming off here. I would predict under these conditions E2 mechanisms for both secondary and tertiary. Now for our tertiary benzyl and allyl substrates, again, we can't have backside attack. So under these weakly basic conditions, we're going to predict SN1 and E1 mechanisms to compete. And I think this is the hardest spot to fill in on the chart. I think under these conditions, it's really hard to know. We'd have to look for electronic effects, extra stabilization from groups being on our allyl, and weigh all of that. But here, I think this is the diciest part of our table, and that SN1, E1, and SN2 mechanisms are all possible, and we'll have to consider those other points that we learned. So I hope this chart helped you glean some information about the reactivity patterns. The top part in particular has a very distinct pattern that we can see from the colors. And I hope this video helped you come to grips a little bit with all the subtleties in the allylic and benzylic substrates that makes these just more complicated examples. I hope you learned something. If you did, please like and subscribe.